Hello, in this video we will compute the length of certain arcs on the hyperbolic plane. But I wanted to start with a word of caution in the way we use terminology when referring to circles, line segments, geodesics, and so on. As you see, the title here has the word circles in it. However, there are two different things we can call circles in this situation. First of all, we have our planar representation of the hyperbolic plane, which is just the upper half plane, and I can draw a circle that looks like a circle on that upper half plane that need not be circle in reality of the hyperbolic plane. So when I say circle, I may sometimes mean the former and sometimes the latter. In this case, when I say circles centered on the x-axis, I do mean circles that I do mean curves that look like circles on the planar representation of the hyperbolic plane. I do not claim that these are actually circles in the sense of a hyperbolic plane. A circle in the sense of hyperbolic plane is of course a locus of points on the hyperbolic plane that are equidistant from some given point. For that to be able to actually see what circles on the hyperbolic plane look like, the hyperbolic circles, I need to know how to measure, I need to know essentially what geodesics on the hyperbolic plane look like first. So I will try to be careful and always say which ones I mean. However, sometimes you need to deduce it from the context. So when I will say circle, a line segment, I generally will refer to things that look like that in the planar representation of the hyperbolic plane. When I want to say a circle, an actual circle on the hyperbolic plane that may not look like a circle for us, I will try to say hyperbolic circle. And the same thing with triangle, and instead of when I want to say line on the hyperbolic plane, so that really means geodesic on the hyperbolic plane, I will try to say geodesic. Okay? So in this case, the circles I'm talking about are not circles, are not hyperbolic circles. They are just what looks like circles to us. So here is the hyperbolic plane. With the x and y axis, and I pick a point somewhere on the x-axis. Let's say the coordinates of this point are c0. Note that this point does not lie on the hyperbolic plane because the x-axis is not part of the hyperbolic plane. And then I will draw a circle centered at this point. And the upper half of the circle does lie on the hyperbolic plane. The bottom doesn't. So this is something that the inhabitants of the hyperbolic plane can see. It probably, and you will see soon, it actually doesn't look like a circle to them. But for us, it looks like a circle. In the previous video, we measured length of certain simple curves, namely of straight lines. Now, these were straight lines to us. They were not necessarily straight lines to the inhabitants of the hyperbolic plane, because we will not know what straight lines are to the inhabitants of the hyperbolic plane until we compute what geodesics look like. We're not there yet. However, this actually turns out to be a quite nice and simple calculation. So I can actually compute the hyperbolic length of an arc of such a circle. So suppose I pick 2 points on that circle, P and Q, and so I have 2 rays. Again, just to remind you, if there was an inhabitant of the hyperbolic plane standing at the point C and looking towards the center of the circle, they would never be able to see it, because that's like infinitely far away from them. Same here. So I am interested in this length. So I'm going to to color this in purple, I will call this C. Okay, and here I have a certain angle, theta. So the question is, what is the hyperbolic length? Of C. Well, if I just were to write down some parameterization of it, then so if I parameterize C, then I can use the formula for the length of a curve that we discussed last time. So what's a good parameterization of that curve, of that arc? Well, by the angle, right? The angle actually provides you with quite a good parameterization. So if I take any point here on this arc, let's say, oh, that's a good one. If I take any point here, x, then, x comma y, then how can I parameterize this curve? I can do it the following way. X equal to, so let's suppose that this distance here is r, okay? That's the radius of that orange circle. So x would be c plus r cosine t, and y equal to r sine t. So when t is 0, then when t is 0, then y is 0, and x is equal to c plus r. So maybe is equal to c plus r. So that means we're starting off here, right? This is what this point corresponds to t equal to 0. And then we're going sort of counterclockwise this way, right? The point here at the top, that would be when t is equal to pi halves, then y is equal to r. That is really the distance here. And x would be equal to c plus 0, so c, right? And finally, going in the other direction, when t is equal to pi, then y is again equal to 0, and x is equal to c minus r, so we get this point there, right? So the coordinates of this point here are c plus r, comma 0, and of this one are c minus r, comma 0. Okay, so then the length of c in this parameterization would be the integral from, okay, so this angle here, let's call this alpha, to the angle alpha plus theta of the square root. So I guess I can just write the square root a little shorter. So I get dx over dt squared plus dy over dt squared. That's under the square root divided by y dt. Okay, so that's that is a good parameterization of the curve. That is, we start with t equal alpha, and then we go all the way here up to alpha plus theta, and then we trace out this arc here. And with this parameterization, we get this formula for the length of the curve. Okay, so let's compute it now. So what's dx over dt? So that's going to be minus r sine t. and dy over dt, that's going to be r cosine t. So the length is going to be the integral from alpha to alpha plus theta of r squared sine squared t plus r squared cosine squared t underneath the square root divided by, oh, what's y? Well, y is just r sine t dt. So let's continue with the calculation over here. So first of all, you see that I can take out r squared from the expression underneath the square root, and then what I have left in the parentheses is sine squared plus cosine squared. So that thing actually underneath the square root gives me just r squared. Take out r squared, you get sine squared plus cosine squared, so it's r squared times 1. I take the square root of r squared, I get r, and then it cancels with this r at the bottom here. So this length is just the integral from alpha to alpha plus theta of 1 over sine t dt. So that's just an integral of cosecant of t. All right. Let's actually compute what this integral is. This has nothing to do with foundations of geometry. This is just calculus, trying to calculate what you get from this integral. So I'm going to do this quite quickly because that's, as I said, not really part of our course here. So integral of 1 over sine t dt, I can multiply top and bottom by sine t, and then I have sine squared t here, which is the same as 1 minus cosine squared t. And then I can use the substitution, u equals cosine t, so du is equal to minus sine t dt. So I get that that's minus the integral of du over 1 minus u squared. So it's the integral of du u squared minus 1. How do you solve such integrals? Well, you do partial fractions. So if I use partial fractions on u squared minus 1, I get a over u plus 1 plus b over u minus 1. So 1 is equal to a u minus 1 plus b u plus 1. If I plug in u equal to 1, I get 1 equals, so this becomes 0, to b, so b is 1/2. And finally, if I plug in u equals minus 1, I get 1 equals minus 2a, so a is minus 1/2. Okay, so with this, I know that this integral, which was just the integral of 1 over u squared minus 1 is equal to, so a is minus 1/2, so that's minus 1/2 the integral of 1 over u plus 1 du. And then b is 1/2, so that's plus 1/2 the integral of 1 over u minus 1 du. Okay, so that's minus half natural log of absolute value of u plus 1 plus 1/2 natural log of absolute value of u minus 1 plus c, which gives me, if I put it all together, that's natural log of the square root of the absolute value of u minus 1 over u plus 1 plus c. And my u is cosine t, so that's natural log of the radical of, well, because I have absolute value, I can switch the 1 and the u, so I can just write 1 minus cosine t divided by 1 plus cosine t plus c. Okay, so that's one form of this antiderivative. I personally do not like too many trigonometric functions. I think sine and cosine and tangent are enough, but many people actually like many more, and there's also secant, cosecant, cotangent, and if you use here cosecant and cotangent, you can write it slightly simpler. So let's see how you can do this. So if you multiply this fraction, which now has both top and bottom positive, by 1 minus cosine t over 1 minus cosine t, then you get 1 minus cosine t squared in the numerator, and this becomes 1 minus cosine squared, which is the same as sine squared. Okay, and that allows you to remove this radical. So the integral of 1 over u squared minus 1 du is equal to natural log radical of that, so that's natural log of 1 minus cosine t over sine t, which is the same as the natural log of 1 over sine t, that's cosecant, minus cotangent. Okay, enough of that calculus. That calculus just gives me the value of this integral, so this is the antiderivative here. So I get that this is natural log of cosecant of alpha plus theta minus cotangent of alpha plus theta minus the natural log of cosecant of alpha minus cotangent of alpha. So finally, the difference of natural logs is the natural log of the ratio. So we get, finally, we get that this length of this curve C is equal to natural log of this goes on top and this goes on bottom, so it's cosecant of alpha plus theta minus cotangent of alpha plus theta divided by cosecant of alpha minus cotangent of alpha. All right, if you denote, if you use beta instead of alpha plus theta, then this is just natural log of cosecant beta minus cotangent beta over cosecant alpha minus cotangent alpha. So that's the length of that curve. You can imagine that this arc length is actually a lot shorter than like these bits here, because as you approach the x-axis, you know that the length, the real length in the hyperbolic world become really large. And that's actually exemplified here by this natural log. So I encourage you to compute, to give yourself different angles, different points P and Q, lying differently on this circumference, and just use this formula to compute the arc length between them. But, there's a reason why I kept this picture on the board and tried to sort of work around it, because this formula is quite interesting for another reason. Namely, here's a corollary to that formula. And before I write it, I'll explain it. So, let's look at this picture. And suppose that I take another circle centered at the same point but of a different radius. So maybe, let's just orange colors. Okay, suppose that the radius here is something different, so that this point is C plus some big R, comma 0. Okay, and then suppose I extend these out here and get some point Q prime and get some point P prime here. So suppose you actually are building a sporting facility in the hyperbolic world. On Earth, when you build stadiums for people to run, for people to run on tracks, if the stadium looks like this, and the various runners run on tracks, and suppose this is the finish, and they're supposed to each make sort of one circle around the stadium, then of course the person who's running on the inner track actually has a shorter distance than the one running on the outer track. So usually what you see in various sporting events is that the starting lines of these two people are actually at different locations. This one then has to run sort of that distance to the finish, and that one starts a little bit ahead so that the total distance is the same. So suppose I have two hyperbolic runners, people who live in the hyperbolic plane, and this is the stadium, suppose, at least the sort of the upper part of it, okay? And here is this starting point, P, for one of the runners. This is one of the tracks, and here is the other track for the person starting at P prime. And here are the finish lines. So this is sort of like, without any effort, designing a stadium that is, it's as if I had both of these runners start and end at the same point. So which of the tracks is longer, this one or that one? Well, if you just look at it, it looks like that one is longer than that one. But then a certain suspicion arises, maybe, because you know that the distances in the hyperbolic planes are distorted. So the curves that lie closer to the x-axis are actually longer than the ones that lie further away. So this one looks longer, but that one lies closer to the x-axis. So in reality, the length of this is actually a little longer than what we see. So what are the real measures of these arcs? Which of them is longer? Well, because they're both centered at the same point and have the same angles, I can just use this formula to compute their length. And you look at the formula and you see that the radius is completely absent from the formula. Which means the only thing that matters for any of these formulas, whether I run along this arc or that arc, are the angles. These are the only things that enter the formula, alpha and theta. So what's the conclusion? The conclusion is that no matter how big of a circle I draw, as long as I start with the same angles and end with the same angles, the length of the track is going to be the same. Right? There is no radius here. So the length of this curve is given by this formula, because you start at the angle alpha and end at the angle theta. And the length of this arc is the same. You start at the angle alpha and you end at the angle theta. So you get exactly the same formula. So the corollary is this: two circles so given two circles centered at the same point, on the x-axis, the hyperbolic arc length between two points. Okay, this is becoming complicated. Given two circles, C and C prime, centered at the same point on the x-axis, the hyperbolic length between points A, B on C and the hyperbolic length between A prime, B prime on C prime, I'll continue down here, is the same as long as, let's see, so the angle, this angle has to be the same, right? So we have to name the centers, given two circles, centers at the same point. What's a good name for a center? C, but I already used that, so maybe P. As long as the angles ACB is not C, APB is the same as the angle A prime P B prime. You know what? Let me just make maybe this notation the same as the one on the picture. So given two circles, C and C prime, these are the two orange circles, centered at the same point. Let's call this point actually maybe A on the x-axis. The hyperbolic arc length between P and Q on C, and the hyperbolic length between P prime and Q prime, P prime and Q prime on C prime is the same as long as the angles PAQ is equal to the angle P prime AQ prime.